We've been making a fairly logical progression through chapters during the semester so far. We're now at week number 7. We've covered 6 chapters so far. The first 2, chapters 1 and 8, dealt with measurement and calculation, so we didn't really get into any chemistry at all at the beginning. In chapters 2 and 11, we talked about the nature of matter and atoms. What are atoms made of? What are elements made of? And we learned about the elements on the periodic table. That's the building blocks of chemistry. To an elementary school student, our periodic table of elements is like the alphabet. That's the letters that they learn, so those are your letters. In chapters 3 and 12, we put those letters together. We took the elements and we combined them together and we made various chemical compounds. If you were in elementary school, after you learned the alphabet and you learned how to make words out of them, the next logical thing you would do, of course, is to make sentences. And to a chemist, a sentence is basically a chemical reaction. This is one of the first chemical reactions we're going to talk about during chapter 4. And I have a very fun demonstration involving that chemical reaction and this little tank of hydrogen gas over here. We're going to be blowing some hydrogen up here in a little while once we get farther into the chapter. We talked about how to recognize chemical reactions a bit back in experiment number 7, which we did a few weeks ago. And we learned that color changes, precipitates, bubbles, change in taste, change in smell, those were all good indicators of chemical reactions. And I thought it might be nice to start out chapter 4 by showing you some evidence of chemical changes and the rare cases where we think a chemical change is occurring and it's actually not. So let's start out with a beaker of water, and I'm going to add some yellow food coloring to it. Right now the water has no color. Let's add a couple of drops of yellow food coloring to that. We'll stir that up and oh heavens, it turned yellow. That's not a big surprise, is it? Was that a chemical change because the color changed? The answer, of course, is not, because it was already yellow. We didn't change the water yellow. We simply added some yellow molecules to the water. So normally we would always say a color change is a chemical change, but that means the color actually had to change. Now what happens if I add a drop of blue food coloring to the yellow? Let's go ahead and stir that up and like, holy cow, it became green. Now that's probably not too surprising. You learned back in kindergarten probably about how you could mix various colors together. So when I mixed the yellow and blue food coloring together, did a chemical reaction occur? The answer is no. Because we've learned in the past that when you mix blue and yellow together, your brain perceives that as green. We didn't make a new chemical compound that happens to be green. We simply mixed 2 colors together and our brain perceives it as green. As far as quizzes and exams go, I'll make it real easy for you. If there's a color change, it's a chemical change. I just had this as sort of one little counterpoint to show how you could apparently have a color change and not a chemical change, but the fact is it didn't really change the color. We simply blended colors together. Let's try another colorful reaction and see if this one is a chemical change. I've got some water again in my beaker, and I'm going to add to that some phenolphthalein. Phenolphthalein is what we call an acid-base indicator. It's a compound that changes color when the solution changes from acidic to basic or basic to acidic. We'll be using indicators in some experiments later in the semester. We haven't quite got to that point yet. So let's go ahead, we'll stir that up, and you'll notice right now it's colorless. Let's add first a little bit of ammonia. Ammonia is a base, it says right here, basic clear ammonia, so it's obviously a base. I'm going to put a little bit of ammonia into that water, and ooh, look at that. It turns this lovely pink color. That's the color that phenolphthalein becomes when the solution is basic. Now, was that a chemical change? In this case, absolutely, because the phenolphthalein had no color to start with. The ammonia was colorless, the water was colorless, yet now we have this lovely pink color. A color has appeared that was not there before. Color change, definitely a chemical change. When you add a base to the phenolphthalein molecule, it undergoes a chemical reaction. It changes its chemical structure just a little bit, and that new molecule happens to be pink in color. Now, interestingly enough, although people don't often realize this, chemical changes are reversible. You can make them go in reverse. I'm going to take a little bit of vinegar, which is an acid, and we'll add that to our solution to convert the basic solution to an acidic solution. That looks like it might be enough. Let's find out here. And lo and behold, look at that. The phenolphthalein is reverted back to its acidic form. Color change, another chemical change. We could keep doing this over and over again. I can add some ammonia back to it again. Let's see, a little bit more there. There we go. We can make it pink again. So this is an example of a very easily reversible chemical change. Some chemical changes are a little more difficult to reverse, but this happens to be a very simple one. So this represents what we would normally assume. If you have a color change, you've got a chemical change. All right, we've looked at color change, so let's take a look at a different kind of chemical reaction and see if you can tell whether or not a reaction has actually taken place. This time we're going to combine some salt and 7-Up. I feel bad I keep wasting these soft drinks. I used a whole bunch of Coke in our opening day demonstration here, but it's all for the cause of science. All right, so there's our 7-Up. It bubbles a little bit, which is normal. Now let's add a little bit of salt to this and see what happens. So watch carefully here. Ooh, look at that. So we've got bubble formation. We learned earlier in the semester that the formation of a gas indicates a chemical reaction. But did a chemical reaction actually take place here? Answer in this case is no, because the gas you're seeing is carbon dioxide. We can add some more salt to it, and it bubbles again. And although it's not obvious to you guys from a distance, there's still a pile of salt sitting on the bottom, but the salt is no longer making it bubble. So we didn't actually make a gas in this particular case because carbon dioxide gas is already present in the soft drink. What the salt did is speed up the natural process. If you open a soft drink, it slowly bubbles and it goes flat. If you add salt, it simply speeds up the process. So the salt is merely a catalyst here. Interestingly enough, it's just the rough surface on the salt crystals that's causing the bubbles to form. Bubbles need a surface on which the molecules can collect and form, and the rough surface of salt works very well. You've probably seen this same kind of thing happen at home. Have you ever poured a soft drink over a glass of fresh ice and it just foams like crazy? Because the rough surface of the ice is causing the bubbles to form. If you drink that first glass and you add some more soft drink to it, it doesn't bubble again. Once the ice has become smooth, like the crystals of salt have, it no longer catalyzes the process. I can add some fresh salt once again, and we get bubbles again, but only as long as the rough surface exists. So invariably, the formation of a gas is a chemical change. The thing here is we didn't actually form the gas, it was already there. We just convinced it to leave the 7-Up more quickly. And here's a quick close-up of the salt going into the 7-Up. You can see it really fizzes initially while the surface of the salt is rough, but as soon as the water dissolves that rough surface away, it pretty much stops. Same thing happens when you put fresh ice cubes in there. Now this is one I'm sure you've all seen and probably done before, and that is mixing baking soda and vinegar. So let's go ahead and add some vinegar to our beaker. And now we'll put in a little bit of baking soda. Watch carefully. And it looks a lot like the salt in 7-Up. We added a clear liquid and a white solid, and we got bubbles. Was this a chemical change? In this case, absolutely. If you think about it, were there any bubbles in the vinegar? Vinegar is not carbonated, so there was no carbon dioxide in the vinegar. Certainly there was no bubbles in our baking soda, so that formation of a gas must have come from a chemical reaction, and indeed it does. The vinegar neutralizes the baking soda and produces carbon dioxide in a chemical reaction, but it looks almost identical to the 7-Up and salt. And just like that, we could also add some more baking soda and make it happen again. This reaction would be a little more difficult to reverse than some of the earlier ones, but it could be done. So, as I said about the color change is invariably a chemical change. Formation of a gas is invariably a chemical change. In the case of the colors, when we mixed the food colors together, we didn't actually make a new color. The colors were already there. But normally, in a case such as the phenolphthalein with the vinegar and the ammonia, we truly did make a new color that wasn't there before. So we can assume color change is a chemical change. With the salt and the 7-Up, we got bubbles, but the gas was already there. We didn't actually create or produce carbon dioxide. It was already present, so that was not a chemical change. But in pretty much any other case, if you see bubbles forming like we did with the baking soda and the vinegar, formation of a gas means a chemical change has occurred. All right, so I hope you enjoyed this little demonstration. Let's go ahead and get back to chapter 4 now, so we can get to the point where we can do this really fun demonstration with our hydrogen gas and our exploding Pringles can.